So I start with two algebras. So I have little a from maybe A to A, little b from maybe B to B.
Yeah.
Up in here. I say that a morphism between these guys should first of all be a morphism, a function between the underlying objects / types that preserves the structure. So I want just a morphism F between the underlying types. Such that when I plug it into maybe, so I do maybe F, that's what this is. This commutes.
I see. You're not saying that there's an algebra morphism for every morphism in the underlying type.
No. Yeah.
But the other way around. Okay.
Yeah. You need to start with the morphism, and then you ask if this special property holds.
Yeah. And it might not for some choice of that.
Definitely. Yeah. Yeah. So like I said, a little a endows capital A with some algebraic structure, and asking that this commutes asks that F preserves the algebraic structure. So why is that? If I think about the inhabitant of this guy's unit, I send it to something in A, which is kind of like the zero element of A, and then F will map that to some element in D. Okay. If I think about it again, over here I have the sole inhabitant of unit. Under this map, it just goes to the sole inhabitant of this unit, and then B will send it to the special zero object of B. So asking that this commutes asks that if I send the special inhabitant of unit over here, this way, and this way, they agree. So I'm saying that if I have the zero object of A, the zero element of A, and I do F to it, I get the zero element of B. And similarly for the successor, that's a bit more complicated. Yes?
And that also amounts to saying that F, AOF or FOA is the same morphism as BO and BF. I don't know how that would work.
Yeah, so if I want to write this as like a diagram, but in line, then I can write that this equals B circle, well maybe I'll just write B cap. Equal to B cap. So this is exactly the same as this, there's different ways of writing it. Yes.
Can I ask if, without asking to go through the details, like with this kind of structure, if I wanted a different reduction principle,
Yes.
or so like if I wanted 0 and 1 or whatever, I mean, it's just a pair of these
Yes.
commutative
Yeah.
relations.
So just replace, if you want different inductive principles for different things, like maybe the next interesting example would be this in some type A, or some object A. You guys have used that before, but this in some object. You just replace the functor maybe everywhere with whatever functor you like that bundles up the structure that you're trying to give to an object.
I meant a little differently though, like if I needed my induction principle to refer to 1, for instance, just, is this okay in this framework?
Yeah, definitely. Yeah, you would just want like 2 units. Basically, you want to say where 0 goes, where 1 goes, and then where the successor goes.
Maybe a family of coproduct types representing the family of induction principles, then you have to have a different coproduct type for each.
Yeah, so your functor maybe would be a different functor. So you could do unit plus A. Okay. All right, so the morphisms between algebras are morphisms of the underlying objects that preserve the algebra structure. That makes sense? Okay. So now, we want to observe that the natural numbers, if we want to define the natural numbers should definitely be a maybe algebra. Like we said, I erased it unfortunately, but we said that we want this structure. We want a 0 and we want a successor in the natural numbers. We also said that if we want to produce a function out of the natural numbers, it suffices to give this kind of data on an object A, on a type A. And we bundle that up by saying that kind of data, and we want to have a morphism or a function like this. It is exactly a function like this. So giving this kind of data for a particular type A or object A is exactly giving it the structure of an algebra, exactly producing this kind of map. Okay. So now we can observe maybe, a category of maybe algebras. We call this alg sum maybe. Now we can observe that the natural numbers is an object of alg sum maybe, and it is initial. Okay, because all the other algebras have exactly this structure, which means that there's a unique morphism out of the natural numbers into any other algebra. Okay. So this is the categorical story that underlies everything about inductive types in a type theory, like rock or the simply type limit functions or something. And other questions? Yes.
So can you make the size ones be like little a before one?
What do you mean by precise?
The object are
So I'm saying that the inductive principle in, let's say, rock of the natural numbers says that given this information, there is exactly one map like this. So actually, you bring up a good point. Let me make a point that I wanted to make my kind of forgot about. So set has the structure of a model of Randall. So in the sense that I talked about models or interpretations at the beginning of the lecture, it's one interpretation. And if we tell this story in this particular model, we can talk about the maybe functor. Then the unit would just be, well, it should still be the terminal object, so it would just be the singleton, instex. We tell the whole story, and then we pretend that we don't have any presuppositions. We just check. We want to check what exactly the initial object is that we get in this category. And we hope that it's the actual natural numbers as studied by mathematicians for thousands of years. And indeed it is. So, and so in here, the natural numbers defined through this whole story is the natural numbers. So in some sense, like if you prove something in a proof assistant about the natural numbers, then this story about what it means, what these inductive types actually are categorically, and the stuff about finding models for our type theories, like Martin-Lipp type theory, the fact that there's one in a set, you put it all together, and you find that when you prove something about the natural numbers in rock, you are proving something about the actual natural numbers that have existed for thousands of years. Yes?
So this was let's say, specific case study for some specific inductive type. So if I wanted to generalize this, I would say an inductive type is or categorical representation of an inductive type is the F algebra, where F is the corresponding functor that does whatever I want to this.
Yeah.
Okay.
Exactly. And as some people mentioned, maybe it was at the beginning of the week, when we do this, so we need a functor like this. We need a functor from one category to itself. Maybe set to set is usually where we like kind of check that things make sense. So functor from set to set. We do this whole thing. We look at the category of algebras there, and we ask if it has an initial object. Not always. Doesn't always have an initial object. So like you can't write any weird thing down in a definition of an inductive type because we don't have like the whole, at least in our favorite model, it's not justified because it doesn't exist. So there's a nice class of functors that do have initial objects always in set and then also was it I think, which are called polynomial endofunctors. So if you want to Google that, there's like an ML page about those things. Yes.
I think I'm just trying to, I guess, confirm a little bit of understanding. With the maybe algebra being initial, if I'm getting that correct, implies that like that's sort of the starting point in some sense of other inductive types that we might want.
So it's just a story about one inductive type.
Yeah.
So it's initial in the sense that we have this category of algebras of just the maybe functor. So they're all looking kind of like the natural numbers, in the sense that they have a zero and a successor. And then we look at the initial object among those natural number like guys, and the initial one, which basically doesn't have anything except for 0 and successors, is the natural numbers. And if we want to think about other inductive types like lists in some given type, then we need a different function here. Yes?
Feel free to comment if this is not a short answer, but is there a way to give like a high-level intuition for the difference between inductive types and co-inductive types in terms of this presentation?
Absolutely, thank you, yes. So you notice that there's the word co, or the prefix co there, which means it's a categorical concept. Okay, yeah, and I need a different color of chalk, but that's okay, so just pay attention. So, this is symmetric. We have a category to itself, so it's not like we could like switch them because I mean maybe we could think that we're switching them, but it's the same. But here we want to talk about co-algebras because this is not symmetric. Okay, this is symmetric. We have an object of our underlying category. There's nothing to turn around there, and then we have this morphism that goes from the functor, our object, to our object. So this is something that's not symmetric. This is the first thing that's not symmetric, so we can turn it around. Okay, let me go right back here. So, co-alg, let me just say, of some functor f, where f goes from c to c. The objects are AA, where A goes from capital A to FA. So here it goes from FA to A. We turn this arrow around. And then the morphisms, I mean, they also can be turned around, but it's relatively straightforward what to do. So the morphisms are still the same, basically. They're underlying morphisms of the first component. And then we need an equation that involves the second components. And now the arrows will just go backwards here. I mean, we don't want to draw it because it would be confusing. But maybe I just go like this. My hands are too chunky. Okay, so these arrows will go backwards, and then we just add this for commutes. So then we have the category of co-algebras. And then we don't take the initial algebra, we take the terminal algebra, or terminal co-algebra, sorry. Then we take the terminal co-algebra, I mean, the terminal object in this category. So for the extended natural numbers, you might know that that's the co-algebra version of the natural numbers. You take the same exact functor, and then you switch these maps. You ask those first commute, and then you look at the terminal co-algebra, and that's exactly the natural numbers plus an extra guy at infinity. And you might know about like lists. Okay, I am always scared of the terminology here, like lists and streams, lists and co-lists, whatever you want to call them. Right, so the co-algebra version of lists are potentially infinite lists. Okay, so they are lists plus streams that are infinite. And for that we have a different functor here. Which is why I think I wrote down, but I don't have any space. So we have a different functor here. When we do this story, it gives us lists. When we do this story, it gives us co-lists. Sometimes called streams. Yes? Yeah.
So would there be either functor like a leading functor?
Yeah.
Okay, I see.
Yeah, so so for lists, if you want to think about this whole story and how it works for lists, the functor is not maybe, so okay. So they want to do lists. We have to do x, so they say for algebra. List and x. So you have some base height of x, you want to take list and x. No, I use x for the I use a for the variable. Okay, I hope I'm not going to confuse myself. So then the function that you want to consider is still a unit. You often need this unit because you need somewhere to start kind of to generate everything. And then you want to do x times a. You want to take an a, so think about the function times a, to unit plus x times a. Yeah, and then maybe you can already see that this guy is terminal. We haven't proven this, but maybe it's obvious that terminal times something is just the something itself. So if this guy is terminal, it's just the unit type. Then this collapses to the maybe function that we already talked about, which coincides with something you hopefully already know, which is that if you take lists and the unit type, That's just the natural numbers. Okay, is there another question?
Yes. The one question I wanted to ask was, why are the morphisms from the natural numbers unique? Because if I understand right, if the natural numbers are initial, then each morphism from the natural numbers is something else. There's only one. So why is that?
So are you asking in this example? Or, I mean, in like Marlowe type theory, it's just like defined like that.
Okay.
Maybe one thing to remember is that I'm saying that functors out of natural numbers are unique in this category of algebras, not in the underlying category of types. So they're unique, like they're the unique morphisms that preserve the structure. If they don't preserve the structure, then we don't have anything to say about what's going on. Yes.
So continue on to that question, when you said like it's the initial in the algebra, in the category like algebra maybe, like for me it's not especially clear why that's the case, but I guess I can prove it myself.
Sorry, what's not there?
It's not clear to me that it's initial.
In the example.
I mean you wrote like the natural numbers is an object of algebra maybe and it's initial, and it's not clear to me it's initial right now just looking at what you wrote.
So, the rules of Randall type theory say that the natural numbers has this inductive principle, which is that it suffices to give a 0 and a successor on some guy A, and then there's an induced map from the natural numbers to your guy A, and it's unique. Maybe you need to prove that it's unique.
Yes, that's what I think. You probably need to prove that as well.
Yeah. So basically, I mean, to prove that it's unique, you just do pattern matching again on 0 and S, but your goal is now inequality.
Okay.
So it's basically saying like, yeah, if it's equal at 0 and it's equal at the successor, then it's equal everywhere. Yeah.
So, this statement or what we've been talking about is specific to modular type theory as we talked about it? Because I think I got a little lost as to whether we were saying something very general or saying something about part of the.
Okay, so saying you have a type theory where you have some notion of inductive type, where you can define the natural numbers. Then it probably looks like this. And then in the syntactic category of that type theory, I mean, basically, the way you define an inductive type in any type theory is just saying categorically that it's the initial object in this category. So just you have to translate the rules. I mean, I tried to translate them all over here. Translate the rules in category theory. It's just saying that it's initial in this category. And to say that the natural numbers is initial in this category where you start with set requires some math.
I think my remaining confusion is why is it important that there is exactly one morphism from n maybe to each other thing? Like why can't there be 2 or 3 morphisms from n to each other thing?
Good question. So, if the natural numbers was defined in type theory, such that there's just a morphism like this, given this data, and not the unique morphism, then the natural numbers could be like, I mean, then the object that you specified is not well specified, basically. Like, it could be the interface. It could be the natural numbers times the natural numbers. I mean, so all those objects will satisfy that induction principle. So you have many, many objects that will satisfy that induction principle, and they're not the same in any respect. Or yeah, I mean, well, maybe they're the same in some respect, but you don't want them to be the same. They can be very different, right? So then you won't be specifying the natural numbers as closely as you want to. Then you're going to be programming with something that has crazy behavior. Yes.
Okay, so it's the F is there's a unique F for each pair of these two case functions. But like there could be other arrows between N and A that are based on some other pair of case functions.
Absolutely. So A could be the natural numbers itself. we know some data like this, when natural numbers itself, it is the one that defines natural numbers. If we plug that in, that will give us the identity. If we instead take the natural numbers with the successor being same as always, but the 0 now being 1, then we map the natural numbers like we just add 1 to everything. Or we could do it to be any natural number, and then this function will just be adding whatever that natural number is. Yeah. Okay, so I just want to sum up by saying that this underlies, as I said, the categorical theory of inductive types. Maybe I also want you to notice the similarities with the syntax that we talked about before. So you might know or have a feeling, for non-categorical reasons, that syntax and inductive types are kind of the same. They're both defined inductively. Like all the programs that we can write in a given language is generated inductively by the constructors of the language. And the constructors are some kind of algebraic constructors, just like here. Okay, so the fact that the syntactic category is initial in some category, and the fact that the natural numbers is initial in some category are really instances of the same fact. Right? That the inductively generated thing is always initial in its category of algebras. So you could say that when I define this category curly M, the models of the type theory, I could have also called the algebras of the type theory, because the type theory, most of the type theory is described by lots of kind of algebraic operations. So the models are really algebras for the type theory, and the syntax, the inductively generated thing by all these operations, is the initial one. Just like here. It's really the same thing. Okay, and maybe I just want to end really quickly with some references. So if you're interested in the category theory behind Lambeck's theorem, I would point you to this book, Lambeck and Scott, called Higher Order something or other, Intro to Higher Order Categorical Logic. This book has an introduction to category theory in it, so you don't need any background to read it. Then I think a lot of the similar ideas are contained in lecture notes from Torsten Altig here, who gave recently and maybe for many previous years introduction to category theory in the Midlands Graduate School. So it's called Category Theory for the Lazy Functional Programmer. So I'm taking one of these because now in this lecture I request found out functional programming and good approach. So this is a good one. And then there's a textbook for a master's course at TU Delft by Arons and I'm not sure I can remember exactly how to spell his name. And Bullard, which is category theory for, I think this is called category theory for programmers, but it's really, it's a textbook, so there's a lot in there, but it's really introducing like the minimal amount of category theory needed to explain a lot of the concepts behind Haskell and the things that the students at that university have seen in their functional programming courses. Okay, so questions? Yes? Oh. Yeah, probably in some sense, yeah. The category of authors. Yeah.
Is there anything, I think I've asked on the Slack, is there anything that's formalized, like a textbook you could work through and then interactive rubric?
I don't know about a textbook that's formalized. There is a chapter about category theory in the HOT textbook, the HOT book, if you're interested in HOT. I think I saw some discussion that in the One Lab, that's also based on HOT, I think. So there's also